Dear participants, welcome to lesson number 9, your quantitative and qualitative methods course. Next, we will look at the agenda for today's topic. Today, we are going to talk about hypothesis testing. This is a very important and fundamental topic because it is the subject that will help us understand procedure for validating, or in other words, accepting or rejecting a null hypothesis. In this sense, we will be able to conclude everything related to a statistical analysis of certain data, gaining empirical knowledge that allows us to make business decisions. Next, we will look at the content. Content we will cover includes the following points. First, we will talk about the concept of a hypothesis. What do we mean by hypothesis? What is its definition? Next, we will talk about the steps that we will establish for hypothesis testing. After that, we will talk about the types of errors that one may encounter when conducting the analysis. Next, we will review students' t-test for hypothesis testing, which will mainly refer, for example, to the mean or the difference of means, whether for groups that are, let's say, paired or independent. And we'll conclude with the insights from the session. Well, having mentioned all this, let's get started. Well, what is a hypothesis? A concept of a hypothesis is not foreign to us, nor are we talking about a completely esoteric concept. Are we? Moreover, it is a word, a term that we can usually apply in common vocabulary. Right? Regarding hypotheses, for example, and we observe that the sales of a company are declining, we ask ourselves why. This may lead us to review some data, consult some people, and check some sources. And based on all that analyzed information, we can suddenly have a hypothetical answer as to why sales are declining. It may possibly be due to the lack of training for the salespeople. Perhaps we are talking about an economic recession, a somewhat difficult economic environment for most companies. Or maybe we are discussing a change in consumer preferences. In conclusion, in all these cases, we have tested a preliminary response that aims to answer the underlying question of why sales are declining. The response that we are trying out, and that aims, at least in a preliminary way, to answer that question, we call a hypothesis. That's right. In this sense, a hypothesis is an assumption or a statement that aims to answer a question we have about a certain phenomenon. In this case, our phenomena will be economic and business related. On the other hand, every hypothesis needs to be statistically tested because as long as a hypothesis is not statistically tested, it will remain simply that, an assumption. And it's not very advisable to build management on assumptions, is it? Business management based on assumptions. There may be a lot of risk involved. Well, in that sense, every hypothesis is formulated to be statistically tested. And what we are going to see today is precisely everything we need to do to statistically test that hypothesis. It is worth mentioning that this process allows us to make decisions based on evidence, on empirical data, and those analyses. And finally, as I mentioned, hypotheses can be accepted or rejected. This is the mechanism and the criteria for accepting or rejecting them. That is what today's lesson is about. Well, the first thing the participant should consider is what the types of hypotheses are. Correct. And there are two types of hypotheses that the participant should be aware of. On one hand, there is the null hypothesis, and on the other hand, there is the alternative hypothesis. We will briefly discuss each of them. Let's first talk about the null hypothesis. The null hypothesis is commonly denoted as H sub 0. And this null hypothesis has a certain nature. The nature of the null hypothesis is that it denies any type of relationship between variables. It denies that one variable has an influence on another, and it denies that the variables can be different. In this sense, the null hypothesis aims to propose the idea that any observation we see in reality and try to explain through a certain phenomenon of certain variables is fundamentally derived from chance, meaning it is essentially governed by randomness, essentially in essence. For example, if we observe that after the training received by the employees, sales have increased or job performance has improved, the null hypothesis would suggest that this improvement either does not actually exist, or if it does exist, is basically due to chance, stemming from uncontrolled situations, and is in no way, for instance in this case, attributable to the training. That's how it is. In this sense, the null hypothesis nullifies any relationship between variables, nullifying any effect of one variable on another. In short, the null hypothesis suggests that any observation or result that seemingly rises from some type of variable, some type of intervention, or some type of empirical scientific explanation, the null hypothesis aims to negate that idea and propose that in reality, that observation may not exist, it may just be an appearance, and in the case that it does exist, it is basically due to chance. That's how it is. Therefore, the null hypothesis in its mathematical formulation is related to equality. That's why you will always notice that the null hypothesis always contains equality, and that needs to be explained. Let's assume, continuing with the previous example, that I want to validate my hypothesis related to the role of training in job performance. Let's assume that after the training, we notice that the workers are doing their jobs a little better. So I am assuming that it is thanks to the training. Okay, to test this hypothesis, I am going to do the following, right? I am going to have two samples. Yes, two samples of collaborators who have very similar job performance, and I am going to measure their job performances, and I will determine that they are indeed very similar. And then what am I going to do? I will apply a training program to one sample and not to another sample. And after I have applied training, I will compare their performances again. What I should find is that despite their performance being similar before the training, after applying the training to one group and not the other, their performance will be different. Furthermore, the performance of those trained should be better or higher than the performance of those not trained. Well, that is what I want to prove. And I'm going to conduct exactly this experiment because what I just described is an experiment with an experimental group and a control group. Well, the first thing that would be proposed in the null hypothesis is that the training had no effect, and therefore the null hypothesis would state that the job performance of group 1 and group 2 are equal. They are the same. And if there is any difference, that difference is, statistically speaking, not significant. And what would that mean? That since they are samples, suddenly that sample parameter can be different. But when I infer their true population parameters, that is, and I infer confidence intervals for the true job performance of the populations, it will not be similar or the same. In other words, there can be differences in the sample, right? But that difference can be diluted. And I infer the population values. So for the null hypothesis, those population parameters are equal, which would imply that the perceived difference in the samples is statistically insignificant. This would establish the null hypothesis. That is why the null hypothesis is related to equality. And on the other hand, I have the alternative hypothesis. The alternative hypothesis, often denoted as H, is commonly known as the researcher's hypothesis because it generally states what the researcher wants to prove. In this case, while the null hypothesis would propose that trained and untrained individuals have equal performances, the alternative hypothesis would state that they're different, whether they are simply different, or the performance of the trained individuals is far superior, or superior to the performance of the untrained individuals. In this case, the alternative hypothesis is mathematically related to the inequality or to the greater or lesser. And that is the mathematical language of hypotheses. The null hypothesis posits an equality, while the alternative hypothesis posits a difference, or a greater than or equal to, or less than or equal to. That's right. In this case, the alternative hypothesis would be that the mean of the trained individuals is higher, or perhaps simply different from the mean of the untrained individuals. Is that clear, esteemed colleagues? Shall we continue? Yes. Let's continue. All right. What are the steps to approve a hypothesis? The following steps must be taken. First, create the hypothesis. We formulate the null hypothesis and the alternative hypothesis, and remember that the null hypothesis is associated with equality, while the alternative hypothesis is associated with difference. Next, I need to define the level of significance. And remember that by this point, this is something that should already be understood. That defining the level of significance would involve deciding what the alpha value is. And what is alpha? 2001. Alpha is the probability that we are rejecting the null hypothesis, even though it is true. Correct. 3. Collect and analyze the data. Possibly for this, we may need to apply surveys. But let's say we might have to suddenly gather information from secondary sources, but in many cases, it involves constructing an instrument, collecting the data, and analyzing them. Analyzing the data would mean executing some test statistic, for example, the student's t-test. For example, we could make a comparison of means. For a student's t-test, in this case, the student's t-test, as we will see in later lessons, the student's t-test has two versions: prepared samples or independent samples. In the example we just mentioned, they would be independent samples. Prepared samples are when I apply a pre-test and then a post-test. In this case, it would have been better if I had applied a job performance measurement to a sample. Then I train him, and after the training, I reevaluate his job performance, a pre-test, a post-test. And then I will determine if there is a significant difference between the two. The null hypothesis states they're equal, and the alternative hypothesis states they're different, or one is greater. And then a decision must be made. This decision involves an old typical decision rule, which is to find the famous p-value. Because if we apply the student's t-test, the student's t-test will generate a p-value as a result. And that p-value is the probability of the probability is. The p-value implies a probability. It does not imply a critical value. For example, the p-value could be 0.2. For example, 0.2. What would a p-value of 0.2 mean? Or excuse me, a p-value of 0.2. Let's assume the p-value is 0.2. If it's the p-value, what would that mean? Would it mean that there is a 2% chance, because a 2% chance of rejecting the null hypothesis being true, right? And that would be fine because we are accepting a 5% chance. So if we accept with a maximum of 5%, which would be something like, let's see, there is a probability of rejecting the null hypothesis even though it is true. Yes, there is. What is that probability we are willing to accept? 5. But if the p-value is 2%, hey, we are happy because we want a maximum of 5%. And since the p-value is 2%, we confidently reject the null hypothesis and would accept the alternative hypothesis. But if the p-value is 0.6, it means there is a 6% chance that the null hypothesis is true, even though we are rejecting it. So, since the reliability we are establishing implies that the probability of rejecting a null hypothesis when it is true is 5% and the p-value is 6%, it means that the probability we are obtaining is greater. So, we rather accept the null hypothesis. So what does this imply? It implies that we are going to compare the p-value with the critical factor, with the critical value. The critical value at a 95% confidence level is 5%. At a 95% confidence level, the p-value is the critical value of 0.05. We'll compare the p-value with the 13 value. If it is greater, we accept the null hypothesis, and if it is less, we reject it. That is the decision rule. It's that simple. Well, and this is where we want to focus on the types of errors that can occur in hypothesis testing, and there can be two: type 1 error and type 2 error. Type 1, as I have mentioned repeatedly, is when we reject the null hypothesis, when in fact it is true, and we control that, because it will depend on the level of confidence that we have. For example, a 95% reliability means that we are accepting that the type I error has a probability of 5%. Right, that's correct. Well, there is also type 2 error, and type 2 error is the opposite. It is the probability of accepting the null hypothesis. And it is actually false. Right? That is, if the p-value, for example, is 0.1, right, then we will accept the null hypothesis. And what if we are accepting it and it is false? Type 1 error is related to alpha, and type 2 error is related to beta. That's how we will see it in the books, right? The bad thing is that we can control type 1 error because it depends on the reliability of the study, but we cannot control type 2 error. Oh no. So that actually depends on the power of the statistical analysis conducted. Well, and for example, it can use ANOVA. For hypothesis testing, it can use students t-test, right? And it will also depend on whether the data is parametric or not. But for example, we could say that one of the most commonly used tests in hypothesis testing is students t-test. And we will use students t-test to compare means, to determine if one group is greater than another, or if they are simply different. Correct. Well, then there's the students t-test for one tail, or for two tails. The one-tailed t-test is used when we are interested in detecting whether there is a significant difference, that is, usand. If what we want to demonstrate is that a sample or a population is greater than another population, we use a specific method. But when we simply want to detect a difference in either direction, let's provide an example. Suppose we want to know if the training actually had an effect. So I will have two samples, one from the trained individuals and another from the untrained individuals. My hypothesis is that the trained individuals should perform better at work than the untrained ones. I will use a one-tailed t-test. Why? Because in this case, my hypothesis that I want to test has a direction. In other words, what I want to demonstrate is that these are greater than those. But what would happen, for example, if I don't necessarily want to show that one is greater than the other, simply that they are different? They are different. For example, I want to know if people with different study habits have different performances. For example, there are some people who study with videos and others who study with books. I would like to know if the study habit somehow generates better or worse academic performance. So I am going to compare two samples, sample 1 that studies in one way and sample 2 that studies in another way. In this case, I am not interested in knowing if one is better than the other. What I would like to know is if there are differences if one is better than the other, but either one. In this case, we would be talking about a two-tailed students t-test. That's right. Very good. So, what are the steps to perform students t-test? Formulate the null and alternative hypotheses. Calculate the test statistic. Obtain the p-value and compare it. If the p-value is greater than 0.05, we accept the null hypothesis and that the null hypothesis suggests differences. And if it is less than 0.5, we reject the null hypothesis. What does that mean? It means that there are differences. That's right. Well, and so these are the conclusions of the session. To summarize the process, what do we need to do? Well, we need to formulate the hypotheses. Null hypothesis, which you should remember, states that there are no significant differences between the groups. The null hypothesis is an equality, and the alternative hypothesis could be in two ways. There is a difference without establishing which is greater, or establishing that one is greater than the other. In the first case, I would use a two-tailed students t-test, and in the second, a one-tailed test. choosing the significance level, which is establishing the probability of committing a type 1 error, at alpha, which is usually set at 5%, for 0.05. Then collect the data, process it, apply the one-tailed or two-tailed test with certain degrees of freedom, obtain the p-value, and compare it with critical value, which is commonly 0.05. If it is greater, we accept the null hypothesis. If it is less, we reject it. And esteemed colleagues, that would be all for today. I hope that the session was understood, that you enjoyed it, and that I will see you again at another opportunity.